Yeah, hey folks. So today's the last day of our tutorial series on BCL and BCL Rosetta. Today is a slightly different topic because we're not really talking about small molecules anymore. Today is going to be about non-canonical amino acids. And so a bunch of people in the Rosetta community have done a lot of good work on non-canonical amino acids, Doug Renfraw and Vikram Mulligan, and I think Andy Watkins as well. So a lot of senior developers have made awesome contributions, and I know there are more people than just them. But yeah, so what do we have to offer for non-canonical amino acids? One of the things that is convenient about the BCL is that it has a lot of functionality related to substructure comparisons. And it turns out we can actually use these types of substructure comparisons to make it easier to create the files necessary to generate non-canonical amino acids, as well as supply a sort of rapidly generated Rhodamine library using the conformer generator. And so there are a number of ways in which you can get non-canonical amino acid rotamers. Make-Rotlib is one of those great options. Vikram and I and Mamoon and a couple other people are interested in Rosetta QM, and so there's an implementation for that right now. So there's lots of projects about how to make non-canonicals and make rotamers for these non-canonicals and et cetera. What we're going to show you today, and what Oahn is going to lead the talk on, is a protocol that we use a lot in the Meiler Lab because it's fast and it's easy, and it actually gives similar distributions to what you might get from Make-Rotlib based on our sort of preliminary benchmarking. So this is going to be how to use the BCL to automate your non-canonical amino acid parameter generation process. So that way you can pump out a bunch really fast and easy. And then as part of the tutorial, you'll also go through sort of this exercise of generating a target-specific non-canonical library generation. And so the idea is you can design non-canonicals in much the same way you can design small molecules. And then once you optimize the non-canonicals of interest for a target, you can then go back and create the params files for those and hook them into your proteins and run simulations. And so we're going to walk you through this whole process. Starting with, Oahn's gonna tell us about it. So thank you, Oahn.
Thanks, Ben, for the introduction. Okay, so I will start sharing screen now. Yeah, so I will talk about, I will walk you through the how to incorporate non-natural amino acid into Rosetta peptide design using the tool that available in BCL and BCL Rosetta interface, and then we gonna practice the protocol on the system of a protein peptide complex, which is the enzyme cowpain and cowpastatin complex. So the current, status of designing protein with non-natural amino acid right now in the Rosetta database. So the Rosetta community now have, have the access to the Rhodamine library of 20 natural amino acids and around 100 non-natural amino acids that are available in Rosetta database. And then we using the current the protocol that we're gonna introduce you in the tutorial 8, we be able to we can rapidly generate the Rhodamine library and param file for around 300 non-natural amino acids that are commercially available. And they all alpha non-natural amino acid. But in the future, it's still work in progress that we gonna be able to generate the Rhodamine library and param file for the non-natural amino acid with, non-natural backbone, for example, like N-methyl non-canonical amino acids or peptide or beta amino acids. Which gonna improve the chemical space that are available for peptide design. And here is the workflow of Rosetta protein modeling framework if you want to incorporate a new non-canonical amino acid in. So with so each amino acid is considered a building block, and this building block have different characteristics that is described in the Rosetta param file, and the main important part of this building block are connectivity and then specification of Rhodamine library. And then so the connectivity is really requires to specify different the lower connect and upper connect where the residue gonna connect to the next.
All right, so I'm going to try to pick up Richard. If she comes back, let me know and I can exit out. And so we're going to use my LibreOffice, which is not as good. But the idea is you start from some building block, and then the next thing that you've got to be able to do when you're communicating the parameters to Rosetta is indicate some form of connection point. And so in Kevin Drew's original paper, when he described how to do the non-canonical modeling and with different types of backbones, a big part of it was how do you actually go about specifying connection points for the parameters. What we really use the BCL for is this sort of part right here, which is the Rhodamine library generation, as well as sort of automating the detection of these connection points, putting it on L or a D backbone, so controlling the chirality. We use it for detecting certain properties like, oh, is this an aromatic amino acid? Things like that. And so it's sort of a lot of just the handling to reduce the level of manual handling that you have to do. Yeah. You're fine. I finished the slide for you. Keep going.
I apologize for the technical problem. So the current Rosetta protocol to create the Drawbacks Rhodamine library, which is the make-rod lib for people who are not familiar with the Drawbacks Rhodamine library, is essentially a giant table that show you the side chain the side chain Rhodamine propensity given a set of the backbone angles, dihedral angle sets like sci-fi dihedral. For example, here you have different value of the backbone for the serine, and then you have list of the side chain Rhodamine with the probability given the value of the sci-fi, and then we have the mean and standard deviation value of different chi dihedral angles. However, this replication of the Drawbacks library have some drawback, because this style of Rhodamine library is was designed for non-natural amino acid mainly. So when you translate it into non-natural amino acid, there are certain drawbacks, such as like it's hard to represent the non-natural amino acid with more than 4 side chain rotatable bonds. And then sometimes when the non-natural amino acid have the non-aromatic ring, it don't really have a mean to represent that. And then with the current make-rod lib protocol, is pretty label intensive. So it's hard to scale and be able to generate the Rhodamine library and param 5 for hundreds of non-natural amino acids in the short period of time. And then currently in the protocol, they didn't really consider charges. So our current protocol is generating Rhodamine libraries with BCL conformal generation. And you have learned this wonderful software that Jeff wrote, Jeff and Sandy wrote. And then if we treat the non-natural amino acid as a small molecules, then we can use this application to rapidly generate the sample and generate a set of conformer for the non-natural amino acids. However, and then the format of the Rhodamine library is a PDB Rhodamer, which is different from the Drawbacks style, which show the set of the coordinates of the residues. So it's similar to the PDB Rhodamer library format of ligand if you perform Rosetta ligand docking. And then a disclaimer that this is not intended to replace mixed rod leaf or create a Rhodamer distribution that match the canonical amino acid Drawbacks distribution for for a certain application that require that the site, the information of the side change probability given the set of sci-fi angle is important, such as like Rosetta folding, protein foldings application. And however, Ben did some preliminary benchmark, and he saw that our BCL Conf Rhodamine library also sample similar distribution to micro lead in the canonical amino acids, as he mentioned before. So the workflow of building non-canonical amino acid is first you create a dipeptide representation of the non-canonical amino acid. For example, here you can see the dipeptide form of the methylphenylalanine. Here that we add two different cap group into the backbone of the peptide. So we can specify this nitrogen here and this carbon here as a upper and a lower connection point of the residues. And then we generate the instruction to map the backbone atom. And then we also need to compute the residue properties. And then those two tasks can be performed with a BCL application called generate Rosetta non-canonical amino acids instruction. And then next, we generate the Rhodamine library for non-natural amino acids with another application, BCL, which is the conformal generator. And then finally, we use a Python script file that we originally wrote in Rosetta, and then we made various modifications on, and this is the modify to param polymer main.py. So this and then this script gonna convert the Rhodamine library that generated by BCL to and create a Rosetta residue param file in the PDB Rhodamine format. And this script is not currently available in the master brand of Rosetta, but we also provided this script in with the inside the photo of this tutorial inside the scripts directory.
Hey, Owen, real quick. We should definitely make a note for everybody which branch of Rosetta that those scripts are in, and then obviously we can let people know when we merge it.
I will definitely add that into the Slack channel. Awesome. So now let's have some fun, and then we will try to incorporate some non-natural amino acids into this system of the carpastatin like enzyme and peptide complex. So carpin is a calcium ion dependent cysteine protease, and then carpastatin is a peptide that inhibit this enzyme. And then the task that you're gonna perform in this tutorial is if you're gonna try to find the non-natural amino acid mutant for the residue phenylalanine at the position 610 here. So so as you can see, there are the side of the high hydrophobic binding pocket that serves around this side chain. Still have some space for the side chain to expand. So we're gonna try to find better non-canonical side chain that are phenylalanine derivative to better fill in this pocket. And there are gonna be 3 parts. So the first part you're gonna learn how to generate the param file for generate the param file for the non-natural amino acids. And then the second part, you're going to learn how to incorporate the generated non-natural amino acid into the peptide design. And then the last part is a part that you're going to have fun and incorporate some stuff that you learned in the last several days of using the BCL and Rosetta interface to actually perform structure-based design for this phenylalanine red residue, and then repeat the step of generate the param files and incorporate into the design of the peptide again. So let me walk. Do we still have the time, right? So let me walk you through so the first application that I want to show is the moleculegenerateRhodamo non-canonical instruction. So this file gonna take in a input file, which is a set of the phenylalanine derivative SDF file, and then it's gonna output, and then you're gonna give it a prefix to name the output. And I'm gonna show you what is the input SDF file in a moment, but it is a set of phenylalanine derivative non-canonical amino acids, and then it's gonna generate like a different like for each non-canonical amino acid. It's gonna generate a separate dipeptide SDF file, and then in the footer of the SDF file is gonna specify different properties and the indexes of the backbone. And then you can also specify extra properties of the application. So this application only check, like very basic properties of the residue, such as like the chirality of the C alpha, and the charge and whether or not it have aromatic rings. So technically, this HR property is not needed, but I just want to demonstrate that you can add different kind of residue properties, and then you can also generate a set of partial charge to its atom, and then you later can feed in to the modified to param polymer Python, and you can also specify the chirality. For this, you can specify the L or D amino acid, or you can just set auto, which will let the BCL automatically determine the carbon, the CA chirality. And then I highly recommend use the flag explicit aromaticity, which Ben actually added a while ago to really distinguish between the aromatic bond and the normal double bond. And then and there are other functionality, and then to see it, like again, you type help with the help flag, and then you can see all the options. And then yeah, and here in the script photo, we have the mol file to param polymer main.py, and then if you type help, it's gonna show all the option for you, and then in the tutorial it's gonna tell like we're gonna provide the comment line, and then so you can understand different options. I think my time is up, so I will so now we will have time to do the tutorial. And the tutorial gonna be on GitHub for you guys. So Ben just uploaded the file and the script on GitHub, so you guys can just like update your like download the tutorial and have fun. And if you guys have any questions, I'm Ben. Yeah, thank you. Have fun.
Cool.
Thank you.
Thanks, Oahn. Yeah, everybody. So that's it. That's the talk. And so, like Oahn said, we're going to go ahead and stick around while you guys start the tutorial. And if you have any questions on the material, we will be here to help you guys. So good luck. Have fun.